In this video, we are going to solve Cambridge International A-Level 9701 code with paper 4 variant 2 over there. May, June 2025, most latest paper of variant 2 over there. It is paper 4 and structured questions are available in it. And it is a paper of 100 marks over there. All right. And before starting to the solution of this paper, I will say kindly subscribe my channel and so that you can find the latest paper solutions over there. And it will be much helpful for your complete revision, as during the explanation of the solution of the paper I will try to revise the concept behind any question over there. All right, let's start to our question number 1 here, where he is saying calcium nitrate, okay, decomposes on heating. Write an equation on decomposition of calcium nitrate over there. It means it will be broken down into nitric oxide, it will be broken down into calcium oxide, and also oxygen will be released during the decomposition process of calcium nitrate. So I am writing and going with it calcium nitrate NO3 whole twice. This 2 is coming from this +2 and nitrate is having -1, which is coming below the calcium over there, is going to be broken down, and you are getting first calcium oxide, you are getting nitrogen dioxide, which is being taken with 2NO2. Just try to memorize such type of reactions over there so that your products can be memorized over there. Plus 1/2O2 for balancing the chemical equation over there. I have used this 1/2 there. If you just observe there, nitrogen is 2, so I have put 2NO2 over there, and O is 4 from here, 5, and this one is for 6. If I take 2, 3 times 6, and calcium is only 1 over there. So this is the balanced chemical equation over there. Here he is saying describe the trend in decomposition temperature of the group 2 nitrates over there. As we know that down the group, what will happen? Atomic radius or cationic radius. Cationic radius is increasing. So the decomposition temperature will also be increasing. So decomposition temperature is also increasing over there. And we can also add over here that as we look towards the larger size of the cation will be responsible for less polarization because of the nitrate ion, because he was saying group 2 nitrates, less polarization will be available, less polarization will be available due to we can say due to nitrate anions, due to available for nitrate ion, because it is harder to break, because it is harder to break nitrogen oxygen bond over there, nitrogen oxygen bond over there in calcium nitrate case or magnesium nitrate. So I will say group 2 elements down the group are increasing their decomposition temperature along the group down the group over there. Okay. In the next one here, he is saying that 0.333 gram of strontium oxide is completely dissolved in distilled water to form the solution of strontium dihydroxide or strontium hydroxide. The resulting solution is added to volumetric flask made up of 250 cm cube with distilled water. Calculate the pH of the solution at 298 Kelvin. Give your answer into 2 decimal places over there. So I will say here, first of all, I will have to calculate the number of moles of strontium oxide, which here he is taking number of moles is equal to mass in gram over molar mass. If I go for calculation of mass in gram, that is 0.333, and for molar mass, strontium is having its molar mass mr as we can say, what should I take over there? Strontium. Wait a second. Strontium is having molar mass of 187 over there, 87.6, and then I am adding it with oxygen 16 over there. Then it is giving me 103.6. And let's go with it for the calculation of number of moles first. Let's check fraction introduced. Okay, fraction introduced 0.333 divided by 103.6 is equal to, this is equal to 3.214, 3.214 multiply 10 raised to the power minus 3. 10 raised to power minus 3. These are the number of moles depending upon this mass of strontium oxide according to its molar mass over there. So I will have to go for the moles for strontium oxide, for strontium hydroxide, to make by using these number of moles. If I look towards their concentration of hydroxide ion, it means it is doubled according to formula. So I will say here moles of hydroxide ion into the solution will be taken as doubling this number of moles. 2 multiply 3.214 multiply 10 raised to the power minus 3. It means I will have just to go multiply by 2 over there. Then it is this, and I can write it 6.4 multiply 6.428, 6.43 multiply 6.43 multiply 10 raised to the power minus 3 mole over there. So this was the moles of moles of hydroxide ion to be taken in 250 cm cube. Then I will have to take as I look over here that it is 250 cm cube is the solution, is made up of 250 cm cube. If I take for dm cube over there, then I will say that moles of in 1 dm cube will be 251 by 4. So I will have to go for 4 times for this concentration. 6.43 should be being multiplied by 4, because 250 cm cube multiplied by 4 will give me 1000 cm cube. That will equal to 1 dm cube. If I go for 1 dm cube, then I will say here that the molar concentration in moles in 1 dm cube as molar concentration should also be multiplied by 4 over there to get moles of hydroxide ion in 1 dm cube. Let's check, multiply by 4 over there. Then I will get 9 over 350, that is 0.0257. 0.0257. This is the number of moles in 1 dm cube solution over there. Now I know that if I divide it, this molar concentration, as we know that the product of concentration of hydrogen ion and percentage concentration of hydroxyl ion, then it should be being taken as 1 multiplied 10 raised to the power minus 14 for the pH product of hydrogen ion and hydroxyl ion as a product of water concentration over there. If I am getting this OH negative ion with the concentration in 1 dm cube by 0.0257, if I divide it on the other side, then I can get the hydrogen ion concentration over there. Then it will be 1 multiplied 10 raised to the power minus 14. It is being taken at 298 Kelvin. Okay, this is a room temperature, 25 degrees centigrade is taken 298 Kelvin over there. Then for hydroxyl ion, I will write it here 0.0257 over there. And if I go with the this value, means 1 multiplied 10 raised to power minus 14. Okay. Here I will say 1 multiplied 10 raised to power minus 14 divided by answer. I will divide it by answer. Wait a second. I will have to take it down. Divided by answer over there is equal to 3.8 multiplied 10 raised to power minus 13. 3.89 I am taking here. 3.89 multiplied 10 raised to power minus 13. And if I go for the calculation of POH by taking negative log of OH ion, I can also go for that. Okay, directly being taken by this moles concentration over there can be taken. But if I'm taking the negative logarithm of hydrogen ion pH, it is equal to negative log of hydrogen ion concentration. Then I will say here negative log of hydrogen ion concentration is 3.89 multiplied 10 raised to power minus 13. Then I am taking here again negative means minus log. Wait a second. This was the answer is equal to this. This was the answer as 0.0257. Then I took this to divide 1 multiply 10 to the power minus 14. 1 multiply 10 raised to power minus 14. I got it. And I said divided by answer to get this answer over there. Now I am saying take minus. Why I am taking the long? Okay, I have to put it again, no problem. Negative log of, we have the value 3.89 10 is for minus 13, 3.89 multiply 10 raised to power minus 13, 13 bracket close, is equal to 12.41. This will be the pH of your solution over there according to negative log of hydrogen ion concentration. So pH will be 12.41. Okay, this is the way how I went for it. First of all, I calculated number of moles. Then I took number of moles for OH ion according to formula. Then I took according to concentration. Then I used that concentration as a solubility product between hydrogen and hydroxyl ion. Then I calculated the pH over there. When the okay, let's move to question number 2 over there now. Now he is saying that when cobalt sulfate COSO4 is dissolved in distilled water, all right, a solution A is formed. Okay, then it will be like because cobalt is belonging to a transition metal, then it is having +2 ion over there. And he is saying the reaction scheme is shown that the reaction of solution A. Solution A, what is solution A over there? Then it is just the compound which will be surrounded by, we can say, water ions over there. So I am taking it as the central atom. Then I will say that it is cobalt having how much charge is there? Charge is for cobalt. If I take SO4 as -2, cobalt is having +2 over there. So I will say this +2 is coming outside, and the water molecules which will be attached with it will be taken as H2O with 6 ligands and having the charge on it +2. And for the color, cobalt containing this species, I will simply say here that it is having the pink color. So you should memorize it from the transition metal colors when they dissolve in water over there. And this is just like a physical combination of the cobalt sulfate with water. So it is having no type of reaction over there. It is just like a mixture to be obtained over there. On the other end, V is going towards B. B is the solid which is obtained by NaOH reaction over there. Then I will say here that cobalt will be also being added because it is NaOH. I will simply say here that sulfate ion is being replaced and hydroxyl is going to be added. Then I will say here that cobalt hydroxide is going to be produced over there. Cobalt hydroxide will be produced, and that will be CO with OH whole twice. The reason behind that, again, that the cobalt is +2 charge over its surface. Then he is saying excess ammonia is introduced according to it. Then I will say here the aqueous solution is being replaced again. Then we will say here that, and what about the color? Color will be blue over there. And for type of reaction, I will say here that for the reaction, if I look, then I will say it is a substitution reaction over there. Or I can say it is acid-base reaction, or I can say it is substitution reaction. Substitution reaction, in which I can say water is being substituted, or I will say here it is precipitation reaction over there can be being taken. I can write it as precipitation reaction. If you want to check from here, he said solid B. This is the symbol that it is a precipitation over there. In excess of ammonia to produce the compound C over there, then as in the start, if you look, 6 water were added. I will say 6 are replaced with the ammonia, then it is going towards CO with NH3 with 6 by having the same charge ratio over its surface, that is +2 being taken over there. And for this one, I will say that it is its color will be like yellow brown over there. I am again and again saying to you, you will have to check from the insert, or you should memorize the colors for different transition metals over there. And after that, for this reaction, I will say it is ligand exchange over there should be being taken for, because water is the ligand and ammonia is also ligand, and it is ligand replacement by showing the excess ammonia addition over there. It means water is in deficient form over there. Now he is saying suggest the suitable reagent for the formation of COCl4 -2 from solution A. Then I will say here, if you look here, solution A is just containing water over there, and you want to substitute that water over there and to add Cl4 with 2 minus charge over there, then I will say you will have to add concentrated HCl so that your water can be substituted, or your hydroxyl ion can be substituted by getting that reaction into simplified form over there. After that, he is saying there the complex ion COCl4 has tetrahedral geometry. All right. The 3d orbitals in an isolated CO+2 ion is degenerate. Or degenerate means they have same energy level over there. And complete the figure to show that relative energies of 3d orbitals in an isolated CO+2 ion and CO+2 in an tetrahedral complex. So orbitals in an isolated ion are in an tetrahedral complex over there. In case of isolated, I will say here that 5 3D orbitals in isolated cobalt have the same energy, and 3 orbitals will have same energy. Means I can say cobalt ion are having the same energy levels. But on the other end, I will say splitting 3 higher and 2 lower d orbitals, and 2 lower will be here in case of isolated. And it is isolated cobalt ion, that 3 will be like this and 2 will be like this for isolated. But if I take in tetrahedral complex, then I will say here the energy of all d orbitals in the complex clearly higher than all the d orbitals in an isolated state. So it will be like this, like this, like this, like this, like this. So they are all are at the same energy level, but they are having the complex structure in that case. And this is the way how they should go over there. In isolated state, why I said 2 will have the low energy level, because they have lost their 2 electrons, and 3 will have degenerate energy levels. But in case of CO plus in tetrahedral complex, I will say all the d orbitals in the complex will clearly have the higher d orbitals in an isolated ion over there. Okay, let's move towards the next one. He is saying draw a three-dimensional diagram to show the structure of complex COCl2 with -2 charge. So it is tetrahedral geometry over there. Then I will say C is CO as a cobalt at a central atom. So it should be adding Cl at the top, Cl here, and Cl here also, and Cl here also is available. This is a complex ion with -2 charge over its surface over there. So that is a complex ion that should be drawn according to its reagents available over there. Now he is saying for H2O2, okay. H2O2 can act as an oxidizing agent or reducing agent when reacting with species that contain manganese. Okay. Table 2.2 shows the potential of some electrode reactions. Okay, MnO2 with water with 2 electrons, MnO2 with hydrogen, okay, 1.22, all right. H2O2 plus hydrogen ion plus electron, 1.78. H2O2 with OH with 2 electrons, 3 OH, okay. And oxygen is given, all right. Now he is saying there that how he should be going. One reaction in which H2O2 is acts as oxidizing agent, and one reaction in which it is acting as a reducing agent. Include the values of standard cell electrode potential and overall equation for the reaction when H2O2 acting as an oxidizing agent. Okay, for oxidizing agent, then I will say that if I look on the values over there, then I will say that MnOH whole twice, this compound is being taken, and it is being converted from its value of +2 to be taken as Mn +2 over there, and H2O2, if I take for that purpose Mn +2, H2O2 is being taken as an oxidizing agent, then I will say here that the electrode potential between MnO +2 and H2O2, both of these cases, 1.78 minus 1.22. 1.78 minus 1.22, then the voltage will be this, then the voltage will be 0.56 volt. So I will say here that for this reaction, I will say that it is 0.56. Okay, I'm writing it here. I am saying here it is acting as oxidizing agent with Mn +2 ion. Then I will say here that N +2 ion is going to react with H2O2 to give me MnO2. Okay, it is acting as an oxidizing agent. That oxygen is being added to it, and it is oxidizing +2 hydrogen ions. And as I have done the subtraction for you, that is 0.56 volt, then it will be the standard electrode potential over there, and you will get its value as 0.56 volt over there. On the other hand, if I take electrode potential according MnOH whole twice, if I take that, and if I take this one, then minus 0.4, then if I will take it with according to H2O2 with the 2 electrons over there, then I will say here that when it is acting as a reducing agent or like that, then I will say here that hydrogen ion and MnO2 should be being taken for this one. I will say here H2iO2 is acting with MnO2. Okay, it is acting now with MnO2, and it is replacing the oxygen from there to produce Mn ion. So I'm taking MnO2 plus H2O2. Then what is going to form over there? I'm saying here oxygen is lost, and you are getting Mn +2 over there, and you are getting here water and oxygen plus water plus oxygen. You can balance this equation on your own behalf. And then I will say here that now you are being taking your value for this one as oxygen, water, and H2O2 is being replaced for getting this value again. Then I will have to involve this MnOH whole twice again. Then this value I am taking from 0.56 to subtract minus 0.04, and I'm getting 0.52 volt for reducing potential over there. I think so your both concepts behind these given values of electrode potential, which I have taken here 1.78, 1.22, and minus 0.04 as the reducing potential over there to get my both of these values of these required cells over there. Okay, what is he saying over there? He is saying acidified manganate 7 ions MnO4 negative can be used to analyze the content of iron tablets. Okay, by titration, two identical iron tablets are crushed and dissolved in distilled water. The resulting solution is made up of 150 cm cube with distilled water. 25 cm cube of the solution requires 18.60 cm cube of zero. Okay, acidified MnO4 negative to reach the end point. All the iron ions are oxidized. Okay, MnO4 hydrogen ion 5 electron. Okay, all right. Iron ion, ferrous ion is converted into ferric ion. Describe the color change observed as the end point of the titration over there. Then I will say here that it is being converted, that titration, ferrous ion is converted into ferric ion, and he is saying used to analyze the catalyst of titration and distilled water, and it will be taken from colorless to pink over there. Okay, this is just like a color change, and be being taken on the reaction behalf of half of the reactions to be taken according to manganese over there, and manganese and iron to be involved over there. Okay, let's move now. What he's saying, calculate the mass in milligram. Okay, mass in milligram of an iron in one tablet. Assume that all the iron tablets is Fe plus 2. Show your working. All right, which he has given is molar concentration and the volume over there, which I can use for the calculation of number of moles in case of MnO4 over there, which is being resulting from acidified manganate ion, like in the form of potassium manganate or like that I can take over there. So I'm saying 0.05 and 18.60 cm cube is given, and by converting it into dm cube, I can get the number of moles. As we know, number of moles for MnO4, moles for MnO4 I am taking by concentration multiply volume. Concentration was 0.05 multiply 18.60 cm cube, 18.60 cm cube, dm cube to be converted and divided by 1000. Let's check how much you are getting over there. 0.05 multiply 18.60 means 6 divided by 1000, and you are getting the number of moles as 9.3 multiply 10 raised to power minus 4. 9.3 multiply 10 raised to power minus 4. These are the number of moles for manganate ion. And this manganate ion, if you observe into the reaction over there, is having how many electrons should be given to the iron over there? There are the 5 electrons present. So I will say here these electrons, which moles for iron Fe plus 2 is going to accept, then it will be Fe plus 2 ion should be there for accepting 5 electrons over there. Then the moles of iron ion should be multiplied by 5 by 9.3 multiplied 10 raised to power minus 4. Then I am going with it just to multiply by 5 to my answer. Then I am getting it as 4.65 multiplied 10 raised to power minus 3. 4.65 multiplied 10 raised to power minus 3. And now if I go for calculation of number of moles of iron ions from because it was taken for, if you observe above, it is taken for 25 cm cube over there. And if I want to take it for we will say for 150 cm cube over there, then I will say here, then go and multiply it 150 divided by 25. 25 6 times is 150. So I am multiplying this moles of iron ion, which is taken in 18.60 cm in 25 cm cube. Then I will say I will have to take it in 150. So I will have to multiply 4 for moles. This was for 25 cm cube. Now I need for 150 cm cube moles of Fe plus 2 for 150 cm cube. Then I will say here 4.65 multiplied 10 raised to the power minus 3 should be multiplied by 6. So I am just multiplying it by 6 over there. Now I have got this one, which will be written as 0.079, 0.0279 moles over there, which are present in 150 cm cube of the solution over there. And then I will say now I have the math to calculate in for iron over there. Now I have the moles. I know the molar mass is almost 55.8 like that. Then we can go for mass in grams will be being taken in the form of number of moles 0.0279 multiplied by number of moles multiply molar mass, and that is 55.8. Then I will have to calculate and multiply it by 55.8. This is the MR of iron over there, and it is 1.5566. Then I'm getting it 1.6 gram, 1.6 gram over there. And if I am going to convert it into, as we said, milligram or like that, then I will say this is, if I just observe it, that it is present in basically, we can say two tablets are like that, then I will say here that it should be being taken as and if we observe now, this is 1.6 gram, the mass over there. If I observe here what he was saying about the iron over there, as he said that calculate the mass in milligram of iron in one tablet. So as we have calculated here that there are two identical iron tablets. So this is was the mass of two iron tablets, that was 1.6 gram like that. If I am going towards to calculate for one tablet, then I will say I will have to divide it by 2. So I am dividing it by divided by 2 over there. Then you are getting 0.778. So it is 0.778 gram is the iron mass present over there, Fe plus 2 iron mass present over there in one tablet. And he said give the answer in milligrams. So you will give it 778 because gram should be multiplied by for converting into milli, I will have to go for multiplication of 1000. So 778 milligram is the mass of iron present in the tablet over there. So this was your whole question of 17 marks over there. And if I move to the question number 3 over there, where he is saying define entropy, we can easily say that the entropy is entropy means number of possible arrangements. Entropy it is defined as number of possible arrangements arrangements of particles or molecules over there, particles, and we can also say energy in the system. The system is called entropy of the system. Entropy can be positive, negative, depending upon the arrangement of atoms and temperature over there. All right. Fig 1 shows that entropy S of the pure substance changes with temperature T. Okay, T1 and T2 are shown over there. Okay. Identify the process occurring at each of the temperature where T1 and T2. So T1 is showing the arrangement of the particles to be going to as degradation or more distorted. So I will say it is a melting process in which melting process in which solid is converted into liquid over there. This is the first change in temperature, and the second one where T2 is shown over there from here to here, that it is much larger, as when we say liquid is converted into gas. So I will say here it is boiling. Boiling. As entropy has increased with the increase in temperature, according to the relationship of formula, we also know that temperature is directly proportional to entropy of the system over there. Because it is a negative of delta S is delta Q over delta T with negative sign over there. That is the formula, and we use that relation over there to explain it. Okay, after that he is saying explain why entropy of delta S at T2 is bigger than entropy change at T1. Then I will simply say here that change in intermolecular forces, distances between liquids and molecule will be much larger as than in solids than in liquids. In gaseous state over there. So at temperature T2, the entropy of the system, entropy of system or arrangement of molecules is much distorted over there. Entropy of system is larger because we can say the intermolecular distance between liquids and gases is much larger than solid to liquid, because is larger because distance between molecules in liquid to gas is much larger than, we can say, is much larger than is much larger than solid to liquid over there. Solid to liquid over there. All right. Let's move to the next part here. He is saying the equation of the reduction of iron oxide by carbon monoxide at 450 degrees centigrade is shown. Fe2O3 plus carbon mono plus iron plus carbon dioxide, okay. And Gibbs free energy is given at standard temperature and pressure. Enthalpy changes are showing over there, and now he is saying using the data, okay, he has given for Fe2O3 CO FeCO2 with the enthalpy of formation and standard entropy over there by having the different values always being measured in joule per Kelvin per mole over there. He is saying that calculate the entropy of carbon monoxide at 450 degrees centigrade. For this purpose, we will have to require first to calculate the enthalpy change. And when the enthalpy change is done, then we can say enthalpy of formation can be done. Then we can say we can use the entropy formula to place that and to get the final solution over there. First of all, I am going to, according to the balanced chemical equation over there, if I say here it is 3 carbon dioxide molecule, and then I will say I'm going towards enthalpy of formation, enthalpy of formation over there, delta H with F, enthalpy of formation should be being taken over there. Then I am saying that three carbon monoxide molecules are going to meet with each other with where I can say here three molecules of carbon mono are going to produce three molecules of carbon dioxide. So enthalpy of formation, three molecules of carbon dioxide is having this value. So I'm saying 3 into minus 393.5 is going to be multiplied to get the enthalpy of formation, which should be subtracted from the enthalpy of this 824 over there, and also carbon mono. So for that purpose, I will say that the minus sign is coming over there. Then I am taking here the enthalpy of the reaction. This was the enthalpy of products, and now I am going towards enthalpy of reactants over there. For that purpose, minus 824.2. After that, I am saying here I have three more molecules of we can say carbon monoxide over there, and carbon mono is having value minus 110. So I'm saying here 3 multiply minus 110 should be being taken to get our final value for the total enthalpy of formation over there. And if we go for calculation over there, let's go for it. Okay, here he is saying enthalpy of formation. Okay, place all of these values to get the answer over there. Then it is 3 into minus 393, 3 into minus, okay, 393, 3.5 equals to, this equals to minus 1180 minus, now I'm going towards inside first to multiply 3 into 110. 3 into 110 is equal to this plus 824.2 plus 824.2 equals to this 1154 and minus 1154. So I'm saying here minus 1180 minus minus plus 1154. Let's go for this minus 1180 is equal to this is equal to minus 25.8 kilojoule per mole will be there because all the measurements are calculated in kilojoule per mole over there. For that purpose, now I have to go for the calculation of enthalpy of formation for entropy of the system, standard entropy for of carbon monoxide over there. For that purpose, I will use here Gibbs free energy formula over there, which is delta G at standard temperature and pressure. I will have to take delta G is equal to delta H at standard temperature and pressure minus T delta S at standard temperature and pressure over there also. So for that purpose, I will say here the temperature he has given me there is 450. So 450 should be added with the 273. 450 should be added with 273 over there is equal to 723 Kelvin. So temperature should be taken here as 273 Kelvin. You just remember that it is 450 which is mentioned over there. I am using this formula over there. Now I am putting here the values of my whole values to be obtained over there. Let's go with it. And if we place all of these values to be used over there for this purpose, then I will say here that first of all we will have to go with the to use this whole formula. For this purpose, I will say first of all go for calculation of the values. Your delta G can be taken as 24 25.8 this one, that was the delta HF, the enthalpy of formation over there, that I am taking 25,800. 25,800 is my total energy, which I am taking here with respect to the main value of 36,200. This value, okay, the calculated value and Gibbs free energy, which is given to me. Now I am going towards to add to get that value, and I am subtracting it because it is negative value. So I'm subtracting it from my delta H enthalpy of formation over there. Then I am taking minus 36,200 in joule per mole over there. I have removed the kilo from both of them, from this value and from this given value of the reaction in balanced chemical equation over there. So I am taking here to add my temperature, no, sorry, I want to uh, divide my temperature. Temperature should be divided over there. So overall, I am saying here this 36,200 is going to take, and it should be dividing overall by completely by 723, and 723 is the temperature which was required over there. Then I will say it's all to all is being connected by having its value being arranged over there. Then I will have to take minus 3 times let's check the Gibbs free energy that is uh, available for that purpose. That is Gibbs free energy according to its entropy is being taken as for carbon dioxide is 213.8, minus 3 into 213.8. I have taken for carbon dioxide as its entropy. Then I am taking here for iron as to be formed as enthalpy of formation to be getting 27.3. So I am taking it, iron was, according to balanced chemical equation, was having the two molecules of iron over there. Now I will have to multiply this by 2, 27.3. So I will have to add over here with I'm going to add over here with 2 into 27.3 over there. So all of these values are being arranged. Then I am saying here that I will have to calculate for my I will have to subtract one more, that is minus 87.4, which is from the reaction over there, from the reactants over there. So I will have to subtract this minus 87.4, and as this is subtracted, then I am saying that I will have to go for carbon monoxide, which I want to calculate over there. That is 3 times X, because it is 3 times over there. And then I am saying here that just subtract it with minus 3, and I am getting the amount of that energy in the form of X over there. Just arrange all of these values and the calculator, and you will be simplified by the value of your X, which can be taken as approximately equal to 198 joule per Kelvin per mole over there. I think so your concept behind it should be clarified now. I have properly shown you the exact values which should be implemented to get the standard entropy for the carbon monoxide over there. Okay, let's move to the part D over there, where he is saying that iron oxide can also be reduced to iron by carbon monoxide. Okay, and two steps like enthalpy and entropy is given. State the effect of increasing temperature and the feasibility of this reaction. So I will say as the temperature increases, the reaction will become less feasible, because delta G, like which is Gibbs free energy, becomes less negative and more positive. And due to the product of temperature with the delta S becoming more negative, becoming more minus T delta S becoming more positive over there. So we can use any one of the reason from them. Then I will say as the temperature increases, as the temperature increases, the feasibility visibility of reaction becomes very less, becomes very, we can say, visibility of reaction becomes less over there, and which is responsible for showing that delta G becomes less negative and more positive. As delta G becomes more negative or less positive, I can say. Sorry, less negative and more positive. Less negative and more positive over there. All right. Let's move to the question number 4 over there. Here he is saying that uh, in an aqueous solution, iodide ions react with acidified hydrogen peroxide. Iodine with hydrogen peroxide, as shown. The rate of reaction for reaction 1 is shown. Rate is equal to K into I into H2O2, I into H2O2. Okay. Explain what is meant by order of reaction. So order of reaction is showing the power or exponent to which a concentration and a reactant is raised in an equation over there. I can simply say here that what is meant by order of reaction. I will say here order is basically, we can say, the order of a reaction is the power to which the power to which is the power to which a concentration and concentration of a reactant is raised of a reactant is raised in the rate equation, in the rate equation, as I can show here. A minus I power A H2O2 water power B, like that should be being taken over there to show the reaction over there. After that, he is saying complete the table, the order of reaction with respect to hydrogen ion. If you observe this rate equation, there is nothing to show, no hydrogen ion is present. So according to this, hydrogen ion which is present in the equation is not present in the rate equation over there. Then I can say its order will be 0. Its order will be 0 over there. The order of reaction with respect to I minus 1, if you observe here, I minus 1 is present and its power is 1. So you can say the order of reaction is 1 over there. According to H2O2 is also present in the rate equation here. I am saying here its power is also 1. After that, he is saying overall order of the reaction. So just add both of them and you will get second order equation of the reaction over there. Okay, here he is saying that sketch a line to show the relationship between iodide ion and time over there. So it is first order reaction over there basically. So I will say according to iodide ion, it is being shown in the negative slope form. It should not touch over there. It should be parallel with the horizontal line over there. And it is showing that it is a negative gradient curve. If you take any point gradient over there, it will be a negative gradient curve to show your first order reaction over there. After that, he is saying there, all right, nitrogen dioxide reacts with ozone as shown, and NO2 and O3, O2 and N2O5. The equation of the reaction to rate, okay, 1 powers are given for ozone, and ozone and nitrogen dioxide is given over there. Two experiments are carried out to measure the rate of reaction 2. In first experiment, the initial rate measured is known as the concentration of N2O2 O3. Okay, in second experiment, concentration of NO2 and O3 both increased by factor 4. Okay, predict the initial rate of reaction 2 would change. So they are both are increased by power factor 4 over there. Then I will say the rate will equal to 4 multiply 4, and both should be going for 16 times. The rate of reaction should increase when the power should be increased to 4 over there. After that, he is saying the reaction mechanism for reaction 2 has two steps. Define the rate determining step. Rate determining step, I will say the slowest step of the reaction. The slowest step of the reaction which involves all the possible reactions over there, or mechanism in multi-step reaction over there. The slowest step in the reaction or mechanism in the reaction of multi-step reaction over there. Multi-step reaction. In multi-step reaction, the slowest step is called rate determining step over there. Suggest the equations of two-step reaction mechanism for reaction 2 over there. So if I observe here for reaction 2 over there, then I am saying that first step I am taking that O3 is reacting with NO2 to produce NO3, and then NO3 is going to react more with NO2 to give me NO5 over there. Just look at here what I'm writing: O3 ozone plus NO2. I'm getting here NO3 plus O2. After that, this NO3 I'm taking to react with this one again. NO2 plus NO3 is giving me now for N2O5. O5. If you observe here, this one and uh, this one. NO3 is a reactant to give this. NO2 and NO2 is just like a spectator ion over there, and it should not be taking part in any step over there. So NO2 I can say is being NO3 in both of these cases is not should be involved, and O3 NO2, and I'm getting N2O5, and this oxygen can also be being taken in our overall reaction over there. If you observe there, this O2 is already present. NO2, O3, O2, and 2O5. So NO3 is just like a spectator ion over there. It can be ignored. And this, when I am taking to resolve this reaction into steps, then I have taken this for rate determining step over there. Dinitrogen pentoxide can decompose to NO2 and O2. The rate equation of the decomposition is shown. Okay, only N2O5 is involved in rate determining step over there on decomposition. Oxygen is not involved in that case, and here he is showing that it is a straight line graph over there. So it is having the its value of order of reaction as 1 to calculate the value of rate constant for decomposition over there. For that purpose, I will say here that we should take the simplified form over there, and for that purpose we will use the overall process of this whole reaction. So for this purpose we will have to take the gradient of this whole value for getting our rate constant K value over there. For that purpose I will say here I am taking the value of let's suppose the exact value is for this value is 12, and for this one it is being taken with 4. So I am taking my gradient y2 minus y1 over x2 minus x1. So I will have to take y for 12 multiply, and I will also have to multiply with 10 raised to power minus 4 mole per dm cube over there. Then it is 10 raised to power minus 4 divided by having the molar concentration corresponding to it is 0.04 over there. So for this value, and the corresponding value should be being taken over there, 0.04. Let's go for it. 12 multiplied times power minus 4 and 12. Okay, fraction introduced. 12 multiply 10 raised to power minus 4 divided by 0.04 equals to 3 over 100. So it is 0.03 is the value of K over there. After that, he is saying here, use your answer in part 1, C1, to calculate the half-life over there. So I will say here that I know that And the rate constant according to half-life is having the formula that rate constant is equal to 0.693 divided by half-life. So half-life should be taken as T1 by 2 is equal to 0.693 divided by 0.03. Let's go for it. 0.693 divided by 0.03. 0.693 divided by 0.03 equals to, this is equal to 23.1. 23.1 up to two significant figures is fine over there. Then I can write it 23 over there. Seconds over there or minutes over there can be being taken over there. And the rate is given, and it was the rate of concentration per seconds. Yeah, all right, fine. This was your question number 4. Now I will have to go for question number 5 over there. Chloric acid, HClO, is a weak Bronsted Lowry acid. When chloric acid is added to aqueous sodium hydroxide and an acid-base reaction takes place, as shown over there. All right. Takes place as shown. HClO plus NaOH, NaClO, sodium chloride plus water over there. Okay, identify two conjugate acids and base pairs in the reaction over there. Okay, for the first one, as it is said, acid 1 HClO is being taken as acid 1, then conjugate base for according to HClO, it will be taken as HClO negative. This will be the conjugate base from this acid over there. And for the acid number 2 over there, I can say that there is a water. Water can be taken as here as conjugate as an acid number 2, and its conjugate base can be taken as hydroxide ion over there, can be taken in the both of these cases over there. Here he is saying the value of acid dissociation constant Ka is HClO 3.7 10 to the minus 8. Calculate the concentration in mole per dm cube of HClO at pH of 4.51. Okay, it's easy just to get the concentration into raised to power that to get that value. Okay, then I will have to go for the value to 4.51 to get my concentration for that purpose. So I am saying here, first of all, get the concentration of hydrogen ions over there. So hydrogen ion concentration can be calculated by using 10 raised to power, because we know the pH is negative log of hydrogen ions to be taken as 4.51. It is being taken as 10 raised to power 4.51 over there with negative sign. Okay, negative sign with 4.51. If I take it in power, let's write it 10 raised to power minus 4.51 equals to this 3.09 10 to the power minus 5. 3.09 multiplied 10 raised to the power minus 5. And according to the acid dissociation constant, we need the concentration of HClO. Then in that case, I will write here my value as we know that if we observe here that in HClO the two ions, chlorate ion and hydrogen ion, both should be taken with the power 2 over there. So I'm taking here 3.09 multiplied 10 raised to the minus 5 whole square divided by 3.7 multiplied 10 raised to power minus 8. So I am saying here I will have to go for, this is my answer. I am saying to take its power 2 divided by bracket start 7.7 3.7 3.7 multiplied 10 power minus 8. 3.7 multiply 10 raised to power minus 8 bracket close, and Anything else? Nothing. Okay, should be is equal to 0.02 0.0258 like that. 0.0258, and this is the concentration in mole per dm cube over there. Calculate the concentration in mole per dm cube. So it is concentration in mole per dm cube. For this answer over there will be 0.0258 mole per dm cube. When a solution of HClO is heated, chloric acid and a strong acid not containing oxygen also formed as the only product. Write down the equation of the reaction over there. So I will say here, just go with the HClO. HClO is going to be converted into not containing, that will be HCl, not oxygen containing, and it will be going towards chloric acid to chlorate acid over there, and I will write it HClO3 chloric 5 chloric acid should be being taken as chlorate to be converted, and it will be balanced. How it can be balanced? Like HCl is having oxygen is 3 over there, so I am writing here 3 hydrogen. Here is 1, here is 2 more should be coming over there. Now if we observe the chlorine, total 3 chlorines are there, and hydrogen 3 are there, and oxygen 3 are present over there. So this is the balanced chemical equation over there. After that, he is saying define buffer solution. Buffer solution is a solution where we can say the solution which minimizes the changes in pH, minimizes the changes in pH when small amount of acid or base is added. Small amount of acid or base is added over there. So just a substance that could be added to aqueous ethanoic acid to form a buffer solution. Okay, that is ethanoic acid. And explain your answer over there. Here I will say like hydroxide ion from NaOH, hydroxyl ions from NaOH, which you have used above. Hydroxide ions react with the acid to form conjugate base, react with acid to form conjugate base over there. And in that case, I will say here that when conjugate base is prepared, then you can take that ethanoic acid can also be being taken, and ethanoate, sodium ethanoate ions can be produced. Sodium ethanoate, CH3 COONA, sodium ethanoate is going to be produced by reacting the sodium with ethanoic acid over there, and it is a conjugate base, and it is conjugate base of ethanoic acid. I think so. The reason or concept behind it, you are now clarified completely over there. A conjugate base of ethanoic acid over there. In the part number C over here, he is saying some fertilizers contain calcium dihydrogen phosphate. Okay, calcium dihydrogen phosphate. Okay, dihydrogen phosphate, aqueous solution containing hydrogen dihydrogen phosphate ions. H2PO4 negative can act as buffer solution. Write two equations which show H2PO4 can be act as buffer solution. That's very easy over there. So we can write it over here like how can we write this one to go for equations over there? Then I will say here that CaH2PO4 with whole twice is going to react with, let's suppose we are taking it as a salt, potassium dichromate, an aqueous solution containing the hydrogens will act as buffer. So I am converting this in the presence of water as H2PO4 with 2 as negative ions plus calcium ion over there. Calcium ion, or I am adding it with the HCl over there. HCl, then I am getting CaOH whole twice or CaCl2. Okay, I can take both of them. It's up to me which type of reactant I'm going to provide over there. When this phosphate ion is present, then I'm saying I'm getting it H3PO4 like that, H2PO4 whole with negative sign, and is going to react with H2O, or it is going to react with HCl like that, Cl. Then I am getting here H3PO4, like it is a base, it is reacting with the acid and now being converted into weak acid over there, plus HCl again, or Cl2 again can be taken over there, HCl again over there. So as a reactant we have just converted this and hydrogen is being added over there and chloride ion is produced. So from here in this product he is saying now the solubility product of calcium phosphate is 1.14 10 to the minus 7 mole per dm cube at 25 degrees centigrade. Solubility product Ca with power 3 and PO4 with power 2. All right, Ca3PO4 include the units, calculate the value of Ksp. So as we know, according to value of Ksp, what should we write over there? We should first of all we should say over there that we know that even we are using the product of this or this, then it is having its value, like calcium ions is equal to as Ksp. Then I will say here that I will have to use the whole values to be placed over there. For first of all, I will have to go for this 1.14 being multiplied by 3 as by 3, because calcium is going for that purpose, and I will have to use for 2 times to this one for PO4. So then I will say here that first of all multiply 3 multiply 1.14 1 point, wait a second, 1.14 multiply 10 raised to the minus 7. This is being multiplied as power 3 of calcium ions. Then also multiply with phosphate ion with 2 multiply 1.14 multiply 10 raised to the minus 7. And if I place all of these in values into the solubility product to get all of these values, then I will say it is going to make, let's check over here. Everything is being multiplied, just I'm multiplying it. 3 multiply 1.14 multiply 10 raised to power minus 7 multiply 2 multiply 1.14 multiply 10 raised to power minus 7 equals to 7.76. I think so I should have gone wrongly over there. No, I will have to take this power. Okay, first of all this, then I will have to take power 3 and I will have to take power 2. It means I will have to take power 2 over here, power 2 over here for this value, and bracket start, and for this one I will have to take power 3, and then I will have to place my bracket in the start over there so that I can get my exact value over there is equal to 2.07 multiplied 10 to the power minus 33 means 2.1. 2.1 multiplied 10 to the power minus 3, that is the value, and then he has also 2.1 multiplied 10 is for minus 33 over there, and the unit can be written as mole per dm cube is the basic, but the total power is 3 plus 2 is 5, so mole power 5 dm minus 15. So mole 5 dm 15 mole power 5 and dm cube minus 15 can be taken. Some solid sodium phosphate is added to a saturated solution. Okay, predict the effect, if any, on the solubility of calcium phosphate. Explain your answer. So I will say solubility decreases due to the common ion effect. Solubility decreases due to common ion effect. So I think so this example is clarified by you that both are having the same ions in common, and they can be taken as to decrease their solubility over there. Let's go to question number 6 over there. He is saying methyl benzene react readily with nitronium ion NO2 plus. NO2 plus ions are generated by the reaction between concentrated nitric acid and concentrated sulfuric acid. Write an equation for the formation of Na2 plus ion. For this one, I will say here for this reaction, nitronium ion, okay, is generated with concentrated nitric acid and concentrated sulfuric acid. So I will say here take HNO3, O3 plus H2SO4, both in concentrated form, are going to react with to form all the ions. If I take in consideration over there, then I will say here that nitronium ion plus bisulfate ion, nitronium ion plus bisulfate ion, H2SO4 negative, and one more ion which can be taken is the hydronium ion from the water, because that is also present in case of concentrated solution, and even that is in a rarer quantity. H3O plus can be taken into account. If you want to balance it, you can use the numbers over there. Now he is saying complete the mechanism in which nitration of methyl benzene to form 1-methyl 2-nitrobenzene. 1-methyl 2-nitro means it should be adding the nitro over here, which is being shown over there. All right. Now he is saying nitronium and nitronium ion is being taken. For that purpose, I will say, let's suppose my this nitronium ion is going to attack on this carbon over here like that. Then I will say what should be the carbon number should be added over there. I am drawing the benzene ring again. Benzene ring here. Just observe what I am doing here. I am saying here the hydrogen is available. Here the NO2 is also being added to produce overall positive charge inside, making an intermediate state over there. Methyl is attached, CH3, and this one is also having the benzene ring with alternating double and single bonds over there. When I am saying that this hydrogen is replaced out, then I am saying hydrogen ion should be being present, and your 1-methyl 2-nitro, 1, 2, 3, 4, 5, and 6 nitrobenzenes are should be added over there. Phenol can be nitrated with dilute nitric acid. Okay. Explain why nitration of phenol occurs under milder conditions than the nitration of benzene over there, because we can say that oxygen in phenol like benzene ring with OH group. This oxygen in phenol has a lone pair which is not present in case of methyl benzene. Then I can say here that it has lone pair, it has delocalized electrons. It has delocalized electrons which make the pi system overlaps to which overlaps to give pi system over there, pi bond system over there, and we can say so electron density of the ring is increased. So electron density of the ring is increased. Ring is increased over there, and we can also take that it is not going to show the normal condition as like methyl benzene is showing for this one. Okay, now he is saying that a sample of 2-nitrophenol is reacted with sodium. Okay, complete the equation. Sodium is going to react with it. Then I am saying here that sodium is going to react with this OH group to produce your corresponding salt over there. This, and here I am saying ONA is going to produce, and your NO2 is still present over there. And this is the phenol reaction, like sodium is going to react with alcoholic phenol over there, and also releasing a hydrogen gas. So as we say, the metal reacts with a base, it can produce a salt, and hydrogen gas is released over there. Okay, now he is going towards this whole process in which he is saying 2-nitrophenol, 2-nitrophenol can undergo reaction as shown. Okay, this is on reaction 1, this is on reaction 2, and he is adding NH2 over there. And here he thinks suggest the reagents and conditions for reaction 1 for the production of amine group and removal of this oxygen from nitro group over there. I will say here that we can use here tin, hot tin, we can use for hot tin over there, and we can also use and here concentrated HCl over there. Concentrated HCl will be used to remove the oxygen, and to remove the oxygen from nitro group and adding the hydrogen over there. Okay, here he is saying name the type of the reaction 1. Yeah, this is loss of oxygen and addition of hydrogen. It is called reduction over there. And reaction 2 is carried out at room temperature. Draw the structure of the organic compound of the reaction in reaction 2. Okay, so if I observe here, uh, what is being means acyl chloride, CH3 C double bond O OCl is being going to add the acyl group into the benzene ring. Okay, this is the benzene ring which is having its nitro group already attached, NO2. This is the benzene ring over there. Then I am saying here already my oxygen is present, and now I am taking CH3 C double bond O over there, and then I am saying here attach here with this O with C double bond O with CH3. So you can see here that only HCl is being taken out, which can be written as plus HCl over there, which can be removed from the reactant component, which is CH3OCl acyl chloride. Name the mechanism of reaction 2. So it is nucleophilic addition or elimination. Nucleophilic addition, or we can say elimination. After that, he is saying NO2 group of nitrophenol is electron withdrawing, and suggest the relative acidities of ethanol, 2-nitrophenol, phenol, and water. Okay, for that purpose, I will say here that the pattern of this one, that 2-nitrophenol should be at most acidic, 2NO2 phenol should be there, 2-nitrophenol over there. After that, I will say here then there should be phenol according to acidic, and then there should be water, and at the last it should be ethanol. And for this whole purpose, I will say the reasons can be given that OH bond is like it is due to it weakens the OH bond. OH bond weakens the overall stability. Anion stabilized over there, and proton or hydrogen ion can easily be donated. OH weakens and hydrogen ion easily be denoted over there. And I can also add over here that if we look about 2-nitrophenol over there for this one, then I will say here that it has a p orbital lone pair in oxygen, so its delocalized and overlap system is increased, as I have discussed in the previous part of the paper over there. And for ethanol, it's a positive reduction effect, and electron decanting of alkyl group is also being involved over there, so it is the least acidic over there. So always remember that such type of questions needs the little bit explanations over there. Now he is saying that salt butamol. Salt butamol is a pharmaceutical drug that contains a phenol functional group. Okay, means OH, 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 3OH and NH, and this one is given. Name and classify three other functional groups of salt butamol, which is given. Name of functional group over there, we will say alcohol, or hydroxyl group, which I will say primary functional group, and I will say here alcohol for secondary. How I am writing this, I am just going to explain this now. And for amine, I am saying it is secondary also. If you look for alcohol for primary over there, then this is at the CH2 point where OH is attached. Here it is attaching the carbon which is directly attached with two carbon atoms over there. It means it is secondary alcohol. NH2 is attached with the carbon atom which is already attached with three more carbon atoms over there. So I will say it is also being going for secondary amines over there. Okay, here he is saying metal reacts with bromine. So when it reacts with bromine to form organic product X, draw the structure of X. Then I will say here that as we know that the surrounding positions of OH group and in this benzene ring, I will say bromine just being added, just I'm changing the color to show you there that when bromine is going to react, bromine is going to attach over here. Remaining all the structure of the compound is going to stay the same over there. But on the other end, when I am saying that salbutamol reacts with an excess SOCl2 to form organic product Y, the molecular formula of Y is C13. Okay, Cl2 means two chlorine atoms should be added over there. Then I will take two hydroxyl groups out which are not directly attached with benzene ring over there. Both should be replaced with chlorine, to make this type of structure, to make the formula over there. As he said, Cl2, which was the sign that two hydroxyl groups are going to be replaced over there. Okay, now he is going towards 2-amino butanoate. 2-amino butane. Okay, 2-amino. This is the number 2 carbon atom where amino group is going to be attached over there, and butane exists as a mixture of two uh, enantiomers. Define enantiomers. Means we can say such organic compounds are isomers which rotate the plane of polarized light. The they rotate the plane of polarized light, the plane of polarized light equally in opposite direction, equally in opposite opposite direction. Okay, such compounds are called enantiomers. And explain why the aqueous solution of 2-amino butane has pH greater than 7. Include the equation in your answer. So I will say here, because the amine group or nitrogen can accept the proton, as nitrogen in NH2 amine group can accept the proton. So weak base can be taken over there. For that purpose, he said, I include the equation also. For that purpose, I am writing here CH3CH, CH3CH. Then there is NH2 and CH2, NH2, and again CH2 with CH3, and it's going to react with, I am taking water with it. I am taking water with it plus water, and I am converting it into acidic form with hydroxyl ion also. Then I am saying I will have to take this NH2 with NH plus ion, NH3 plus ion. So I'm taking CH3. Let's go for it. CH3 with CH with NH3 positive with the CH2 CH3 over there, and I am taking hydroxyl ion over there. So this was the way how I should go for this one over there. Here he is saying a 0.1 mole solution of diethylamine has a higher pH than 1 solution of 2 nitrogen. I suggest why. So the reason behind it, that more electrons donating alkyl groups are on nitrogen hydrogen over there. So I am saying here as more ethyl groups are attached, more ethyl groups are going to be attached with directly with the electron donating alkyl groups over there they are having. And on the other hand, I can also say that it increases the electron density on nitrogen. It increases the electron density on nitrogen. Okay, this is the way how to go with it to complete this question over there. Let's go to the part number 3 over there, where he is saying complete the equation. Okay, amine group with acetic acid or ethanoic acid is going to react with, and then I am saying here that it is going to make ethylamine with acetate ion over there. So I am taking here CH3, CH2 with double bond with only one NH2 positive plus CH3 COO negative. This is the reaction which is going to perform. And when I am taking it with acyl chloride over there, then I am saying for acyl chloride that it should be being taken with we can say acyl chloride can be being taken that your C acyl group is being added in place of this CH2. It should be broken down over there. Then I'm adding this acyl group CH3CO completely inside the compound. Then I'm saying CH3 with the CO. Okay, then I am attacking it with NH over there, and N is I am giving to it, and H is I am replacing. And on the other end, I will have only this complete one, and that it should be CH3 CH2 with the whole power 2 over there can be taken into account, plus HCl is enough for this reaction over there. Then he is saying complete the table over there, that this is the monomer, okay, and show the type of polymerization. Okay, CH3, CH3, COOH. So I will say here that it should be being taken as addition polymerization. Addition polymerization. For this one, I will say it should go for condensation, because OH group is attached and this OH is going to lose water over there, and it should go for condensation polymerization. And the first one, last one, he is also the straight chain compound and having amine group also, so it should also go with condensation polymerization over there. All right. Now he is saying ethanoic acid CH3 HC HOOCH. Okay, dioic acid. Ethane dioic acid can react with propane 1,3-diamine. Okay, to form a polymer W. Draw the section of polymer W showing only one repeat unit over there. So on the both cases, I will say C double bond O, C double bond O should be being taken. C double bond O being taken with C double bond O, and it should be taken because amine group is also attached, so it is N with being taken with one H also, and it should be being taken with the remaining other carbon atoms 1 2 3, 1 2 and 3 can be taken. And for the next one you can also go for now to NH again attach. This is N with one H, and on the other end you will also get the monomer, and here you can also get the monomer to get a repeat unit over there being taken into account. Polyalkenes biodegrade very slowly. Explain why. So I can say they are chemically inert. They are chemically very inert over there, and they cannot be hydrolyzed, and their carbon to carbon bonds cannot be broken down over there. Okay, let's move to question number 8 now. He is saying compound A is analyzed by carbon 13 NMR proton and proton 1H NMR spectroscopy. Okay, here it is being showing dicarbonyl compound with, this is the carbonyl compound and this is showing the carboxyl compound over there. And now he is saying state the reference of substance as a solvent used in NMR spectroscopy over there. So I will say here that it can use the TMS as a reference over there, which is tetramethyl silane. That was that if I take silicon as my central atom, then I am saying here CH3 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 tetramethyl silane. This is the reference for this one. And for solvent, I will say it should go for deuterium oxide D2O, or it should take CdCl3 over there. Both you can use according to these values. Now he is saying predict the number of peaks in the NMR of 13 of spectrum of A. So if we observe this, how many peaks we can obtain over there? So it is 1 2 3 4 5, and the last one is 6 peaks should be taken over there. 6 peaks can be taken into account over there. For this whole purpose, and from here the proton, he is saying that the proton NMR for being taken over there. Let's go with it. Spectrum A with the peaks. Okay, 1.10, 1.10. Let's check the graph over there. 1.10, 1.10 not given over there. So I will say here that it will have the number of peaks over there. Let's check some graph is given or not given. Not given. Okay, 1.10 I will have to take for this. I will have to take for this 1.10. It is having how many? That it is having a splitting pattern like CH3, CH2 or CH. So it is 1.10 is coming in this range 0.9 to 1.7. So I'm saying that it is having a we can say triplet triplet as a splitting pattern, and number of protons on the adjacent carbon atoms is 2 over there, and number of 1H atoms responsible for this peak is 3 over there. CH3 are like that. After that he is saying 1.5. 1.5 is being also being taken again over there, and the second one CH3. After CH3 now I'm saying I have to go for CH2 over there. Then I'm saying it is duplet, for which purpose he is saying number of protons on adjacent carbon atoms will be 1, and number of 1H responsible for the peaks is, as we have already mentioned, the 6 peaks over there, 2.85, 2.85. It is 2.85. It is quad, okay. It is a quartet or quadruplet. Quad quadruplet over there, and from here I will say that it is having three hydrogen atoms to the three number of protons on adjacent carbon atoms is 3 over there, and number of hydrogen atom will be 2 again. 3.75 3.75 3.75 3.75, that is multiplied, okay. That is multiplied, that is not having, we are saying that we have to limit it over there. That can be multiple because it can come here, it can come here, it can come here, it can come here, it can come here. There are multiplied over there. So I will say here that it is going towards multiplet, and it is having 6 number of carbon atoms on each side over there, and they are having 1 hydrogen only. Okay, let's move to question number 9. This is the last question of this paper over there. Here he is saying the structure of amino acids of serine and lysine are shown in figure. Okay, this is serine and this is lysine. Okay, now he is saying draw the structure of dipeptide serine. Okay, with molecular formula of this, the peptide functional group formed should be displayed. Okay, it means I will have to take NH2 and COOH to be being participating by the release of one water molecule over there. Then I am saying I'm writing down my all of this formula in the same pattern, and I'm taking my this carbon with COOH. Then I am taking this one with C double bond O, with N with H, and going to write the remaining all the sides exactly the similar as they are present in original form over there, like C with the CH2 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 CH2, 1 2 3 and 4 with NH2 is going to add with this, and I am having here CH2OH, I am having NH2 here, and I am showing H over here. So this was my, and for this carbon atom the other attachments for this one is to attach with this one with COOH, and one hydrogen is also being represented and shown over there. So this is the way you will have to go for this representation of functional group formula display over there. What is meant by isoelectric point over there? So I can say here isoelectric point is the pH at which the pH at which we can say molecule has no overall charge, at which the molecule has no overall charge over there, and we can also say that no net charge is present over there. then we can say that is isoelectric point of serine over there. Now he is saying draw and label three spots on figure 9.2 over there. Okay. And three spots should be being taken to indicate and predict the position of each of these and explain your answer. All right, here I'm taking first of all serine and serlysine. I'm taking the point X is being taken, for example, for me, mixture applied here. I'm saying that my first part is just above it. The second one is slightly above. And the third point I'm saying is also slightly above over there. Here I'm taking lysine. Here I'm taking serlysine. Means both mixtures are there. And for this one I'm taking only serline over there. Let's go for what he is saying. Explain your answer also over there. So I will say here that first of all, correct species are should be drawn over there with positive here and negative here. I have taken over there. Then I will say here that we can take that serline not moved and as a Zwitter ion over there, like serline has not moved from its original position over there. It is exactly there, not moved. Serline has not moved due to its Zwitter ion nature, due to its Zwitter ion nature. And I can also say here that serine, lysine and moves towards the negative as they are positively charged, because serine is positively charged and lysine is also positive charge, so they have moved towards right, towards the negative plate over there. And in the last I will say here that lysine moves furthest because it has the low MR value as compared to the serlysine over there. Here he is saying that shows the synthesis of compound R by the compound by step 1. Here he is saying C6H13NO3 over there. Then I'm saying that I'm breaking this compound over there, and I'm taking with the NH2. I'm opening this one from this point over there. I'm taking here NH2 with my CH2 with my CH, with this point I'm taking now with my OH. And then I am also saying that how should I go for this compound more. Then again CH2, then CH, then CH2, then CH, attached with CH3 with C double bond O, and at the end I am adding here OH group over there, and my compound is completely being broken as a long chain over there. After that, in step 2, he has obtained this zirconium ion. Okay, draw the structure of Q figure is done. Now he is saying state the reagents of the step 1 and step 2. In step 1, where I have just broken it, I will say it is aqueous hydrochloric acid. Hydrochloric acid, that should be taken as aqueous, or I can also take sulfuric acid over there in the form of aqueous solution and heat the reflex over there, and heat reflex over there. And at the end we will say here wait a second, what he is saying. Okay, in step 2 reaction, when I want to convert it into this form where hydroxyl or dehydration is being done over there, then I will say concentrated sulfuric acid and high temperature should be provided. Concentrated H2SO4 and temperature should be provided. Okay, this was the solution of this whole paper. I think so you have enjoyed this and you have learned what the basic concepts I tried to explain in this paper. And I will suggest you kindly revise every paper by making a short notes so that you can easily be able to summarize your final exams over there. Thank you so much for today. See you in the next paper.